Welcome to Foundation Mathematics, Functions, Simple Functions, Inverses, Domain and Range. The objectives for this session are to use a function to describe a mathematical relationship, plot functions and identify the nature of a simple function from its shape, including quadratic and exponential functions, work with the equation of a straight line, carry out simple transformations on trigonometric functions, determine the domain and range of a function and whether it is injective, surjective or bijective, and find the inverse of a simple function. Which letters should we use to represent numbers? In a real situation where the letters represent the value of something known, choose letters reminding us of that thing. So for example, let C equal the number of cats my neighbour has. So in this example, we have 3 cats, and therefore C equals 3. Let's now take a look at a more involved example. Suppose that the only pets my neighbour owns are cats or dogs. Let C equal the number of cats my neighbour has, and let D equal the number of dogs my neighbour has. Then the total number of pets, P, my neighbour has, is given by P equals C plus D, so the number of cats plus the number of dogs. If C equals 3 and D equals 4, then P equals 3 plus 4. So P equals 7. We can also say that the number of pets my neighbour has is a function of the number of cats and dogs they have. When we want to solve problems mathematically, we sometimes need to describe the thing we want to know, which is often a single variable, as a function of something else which might affect it. This lets us combine equations more concisely and elegantly. It also allows us to state what kind of values we can use in the equations. So, for example, there is a formula that converts temperature measured in degrees Fahrenheit into degrees Celsius. So if we write C equals 5/9 times F minus 32, then C is a function of F. But if we rearrange this and write F equals 9/5C plus 32, then F is a function of C. Variables are often represented by the letters X and Y. In the example on your screen, you can see some data about 2 variables, X and Y. Here's the point 13, 26, 39, and 412. We can join these points to form a straight line. This has the equation y equals 3x. Let's now take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's have a go at part A. When x equals -2, y is equal to -2 cubed plus 2 times -2 minus 3. Here, of course, we've simply plugged in x equals -2 into our equation. And then we tidy up to get y equals -15. And then we plug this into our table. Similarly, when x equals -0.5, we plug in x equals -0.5 into our equation. As shown, to give y equals -4.125. Similarly, for x equals 0, to give y equals minus 3. And for x equals 1, we plug in x equals 1 into our equation to give y equals 0. And finally, for x equals 1.5. Plugging in x equals 1.5 gives us 3.375. So plotting these gives us the graph shown. This is minus 2, minus 15. And so on throughout the graph. A mapping will transform one set of numbers into a different set of numbers. For a mapping, the domain is the set of all possible inputs, and the range is the set of all possible outputs. A mapping is a function if every input has a distinct output. Let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. Let's take a look at part A first. The function f of x is defined by f such that x is mapped to 3 minus 2x if x is less than 1 and x squared plus 2 if x is greater than or equal to 1. We are required to sketch y equals f of x and also state the range of f of x. So let's solve this. Here's our sketch. This part is y equals 3 minus 2x, where x is less than 1. And this part is y equals x squared plus 2, where x is greater than or equal to 1. 1 is mapped to 3. Also, although there is a jump, the function is still defined for all x. Also, notice that f of 1 lies on the quadratic curve, so we use a solid dot here. And we use an open dot on the line as shown. Note also that f of x does not equal 1 at x equals 1. So f of 1 is greater than 1, not f of 1 is greater than or equal to 1. And therefore the range is the set of values that y takes, and also we have that f of x is greater than 1. Now let's solve part B. We are required to solve f of x equals 11. So let's solve this. Here's our curve, or here's our function. Here's y equals 11. If we want to solve f of x equals 11, how do we find our solutions? On the positive side, or when x is greater than or equal to 1, or on the negative side, when x is less than 1. Notice that on this positive side, or on the side where x is greater than or equal to 1, we have one solution. So the positive solution is where x squared plus 2 equals 11. And solving this gives us x equals plus or minus 3, but of course we know that the solution is positive, and therefore x is 3. On the negative side, or that x is less than one side, we have one solution also. So the negative solution is where 3 minus 2x equals 11, because for x less than 1, we have this linear equality holding. And solving for x gives us x equals minus 4. And so we have two solutions, x equals 3 and x equals minus 4. The equation of a straight line or a linear line can be written as y equals mx plus c, where of course x and y are variables and m is the gradient and c is the y-intercept. Now let's take a look at another example. We are required to write down the gradient and y-intercept of these equations. Y equals minus 8x plus 5 and 2x plus 8y equals 7. So let's solve part A first. We know that y equals minus 8x plus 5. This is already in the form y equals mx plus c. So the gradient m equals minus 8. And the intercept c equals 5. Now let's take a look at part B. We are required to write down the gradient and y-intercept of 2x plus 8y equals 7. So let's solve this. If we rearrange 2x plus 8y equals 7, so that y is the subject of the equation, we have that 8y equals minus 2x plus 7. Here we've subtracted 2x from both sides. Now we can divide by 8 to give us y equals minus 1 over 4x plus 7 over 8. The equation is now in the form y equals mx plus c, and therefore m equals minus 1 over 4 and c equals 7 over 8. Now let's take a look at another example. We are required to sketch y equals 5x plus 2. Clearly the line y equals 5x plus 2 is linear. So we find any 2 points on the graph and join them. The easiest 2 points to find are usually when x is 0, what's y, and when y is 0, what's x. So let's find out what's y when x is 0. We plug in the values in our line, as shown, to give us y equals 2. So when x is 0, y is 2. That's 1 point on our graph. And when y is 0, let's plug in our values. And rearrange. And finally, dividing by 5 gives us x equals minus 2 over 5. So the 2 points on the line are 0, 2 and minus 2/5, 0. We can plot these on our graph. 0, 2 is as shown, and minus 2/5, 0 is as shown. We simply join the points and we have our line. Now let's take a look at another example. We are required to sketch y equals 3 minus 2x. Pause the video and have a go. Press play when you're ready to view the solution. Y equals 3 minus 2x is linear. So find any 2 points on the graph and join them. The points we're considering again are when x is 0, what is y, and when y is 0, what is x. So let's consider x equals 0 first. So when x equals 0, plug in the values and tidy up to give y equals 3. so one of our points is 0, 3. Now when y is 0, plug in the values again, as shown. Then rearrange to give 2x equals 3. And finally divide by 2 to give x equals 3 over 2. So the 2 points on the line are 0, 3 and 3 over 2, 0. As you can see, we've plotted both of these on our graph. We simply join the points and we have our line. Now let's take a look at another example. We are required to sketch x plus 3y equals 18. Pause the video and have a go. Press play when you're ready to view the solution. Again, x plus 3y is 18 is linear. We find any 2 points in the graph and join them to sketch our graph. When x equals 0, plug in the values in the equation. Rearrange to give 3y equals 18. And then divide by 3. Giving y equals 6. And now find the other point. When y is 0, again, plug in the values in the equation. And tidy up to give x equals 18. So the 2 points on our line are 0, 6 and 18, 0. Let's plot these points. 0, 6 goes here and 18, 0 goes here. We join the points and we have our line. The gradient of a straight line is its slope. It is calculated by dividing the vertical distance by the horizontal distance between 2 points on the line. So for example, if we have 2 points, x1, y1 and x2, y2, and the 2 points are joined by a straight line, then the difference in the y-coordinates is y2 minus y1, and the difference in the x-coordinates is x2 minus x1, and the gradient is y2 minus y1 over x2 minus x1. So change in y over change in x. Let's take a look at an example. Find the gradient of the line which joins the points minus 3, 8 and 3, 6. We can draw a sketch of this just to give us an idea of what is happening if we need some clarity. Therefore, m equals y2 minus y1 over x2 minus x1 as shown. Tidying up, this gives us that m is equal to minus 2 over 6, or minus a third. So the gradient m equals minus 1/3. Let's take a look at another example. Suppose the line joining 3, minus 7 to 8a has gradient minus 2. Work out the value of a. Now the gradient m equals y2 minus y1 over x2 minus x1 as shown. Tidying up gives us a plus 7 over 5. We know that this is equal to minus 2. Now solve for a. Multiplying out, a plus 7 over 5 equals minus 2 gives a plus 7 equals minus 10. And finally, rearranging gives a equals minus 17. We will now take a look at some theory. A straight line is defined by either one point on the line and the gradient, or two different points on the line. Suppose a straight line with gradient m passes through the point x1, y1. If xy is a general point on the line, then the gradient m is equal to the change in y, which is y minus y1, over the change in x, which is x minus x1. So let's take a look at an example to illustrate this theory. Suppose a straight line has gradient 7 and passes through the point 4 minus 1. Find the equation of this line. So let's solve this. In our question, we have one point on the line and the gradient. So for a general point xy on the line, we can say that m equals 7, which is the gradient, equals y minus 1 over x minus 4. Multiplying out by x minus 4 gives 7 times x minus 4 equals y plus 1. And then expanding the brackets gives 7x minus 28 equals y plus 1. And finally, rearranging and tidying up gives y equals 7x minus 29. Let's take a look at another example to illustrate this theory. Find the equation of the straight line passing through the points 2, 10 and minus 1, minus 8. So let's solve this. Now the gradient of the line m is equal to 10 minus 8 over 2 minus 1. This equals 18 over 3, which is 6. So m is equal to 6. If we suppose xy is any point on the line, then m equals 6 equals y minus 10 over x minus 2. Therefore, multiplying out gives the equation shown. And finally, tidying up gives us y equals 6 times x minus 2. Let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. The line y equals 5x plus 2 meets the y-axis at point A. Find the equation of the line with gradient 4 over 5, which passes through point A. So let's solve this. When x equals 0, y equals 2. We can find this by plugging x equals 0 into the highlighted equation. Therefore, the point A is equal to 0, 2. The gradient of the second line is m equals 4 over 5. So if xy is a general point on the line, then m equals 4 over 5, which equals y minus 2 over x minus 0. Rearranging gives 4x equals 5y minus 10. Now let's solve part B. We are required to write our solution to part A in the form ax plus by plus c equals 0, where a, b and c are integers. From part A we have 4x equals 5y minus 10, and rearranging this gives us 4x minus 5y plus 10 equals 0. Let's take a look at another example to illustrate this theory. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. Let A be the intersection point of lines y equals 2x plus 8 and x plus 4y plus 13 equals 0. we are required to find a. So let's solve this. In order to find a, substitute the equation y equals 2x plus 8, as highlighted, into the equation x plus 4y plus 13 equals 0, which is the other equation which has been highlighted. So we have x plus 4 times y, which is 2x plus 8, plus 13 equals 0. Hence, 9x plus 45 equals 0. Rearranging gives 9x equals minus 45, and therefore x equals minus 5, once we've divided through by 9. Now substitute x equals minus 5 in y equals 2x plus 8, as shown. And tidying up gives us y equals minus 2. Therefore, a is equal to minus 5 minus 2. Now let's solve part b. If the equation b has coordinates minus 3, 10, find the equation of the line passing through a and b. So let's solve this. Now a equals minus 5 minus 2 and b equals minus 3, 10. The gradient of the line passing through a and b, substituting into the equation for m, is m equals minus 2 minus 10 all over minus 5 minus 3, which equals minus 12 over minus 2, which is of course 6. And therefore m equals 6. So if xy is a general point on the line, then 6 equals y minus minus 2 over x minus minus 5. Tidying up gives us y plus 2 all over x plus 5. Multiplying out gives 6x plus 30 equals y plus 2, and simplifying gives us 6x plus 28 equals y. So the equation of the line passing through a and b is 6x plus 28 equals y. Now let's solve part c, in which we're asked to express this in the form ax plus by plus c equals 0. Rearranging this equation gives 6x minus y plus 28 equals 0. We are now going to look at some trigonometry. We will begin this session by introducing the definitions of cos, sine, and tan. However, in order to do this, we need to consider a unit circle first. A unit circle is a circle with a radius of 1 unit, as shown in the diagram. For a point P at xy on a unit circle, such that OP makes the angle theta with the positive x-axis, we have cos theta equals the x-coordinate of P, and sine theta equals the y-coordinate of P. We also have that tan theta equals y over x, which is the gradient of OP. Notice that we measure positive angles theta anti-clockwise from the positive x-axis. We will now use these definitions to find the sine, cosine, and tangent of any angle theta. Let's consider this angle theta. As you can see, it is obtuse. However, the definitions remain the same. When theta is obtuse, cos theta, however, is negative because the x-coordinate of P is negative. We are going to use these definitions of cos, sine and tan to generate graphs of sine theta and cos theta. Let's consider sine theta first. We have the unit circle before us and an angle of 45 degrees, as you can see in the unit circle. This corresponds to the value as denoted here. The value 90 degrees is denoted here, and the value 270 degrees is denoted here. We've plotted the points, as you can see. As P moves around the circle, you can plot y equals sine theta by reading off the y-coordinate, as shown. What about cos theta? This time we have the x and y axes as shown. So 45 degrees corresponds to the value here. Next, we have 0 degrees as shown. And now 180 degrees. And we've plotted the points, as you can see. As P moves around the circle, you can plot y equals cos theta by reading off the x-coordinate, as shown. Notice that the point P corresponding to the angle theta is the same as the point P corresponding to the angle theta plus 360 degrees. So graphs y equals sine theta and y equals cos theta are periodic with period 360 degrees. So as we've just mentioned, the graphs of sine and cosine are periodic. We can also say they're cyclic. This means they repeat themselves after a certain interval. We will now learn how to draw these two types of graphs for a given range of angles. Let's first have a look at the sine curve. The graph of y equals sine theta looks something like this. It repeats every 360 degrees and crosses the x-axis every 180 degrees. So for example, at minus 180 degrees, at 0, at 180 degrees, at 360 degrees, and so on. The maximum of the sine curve is at 1, and the minimum is at minus 1. Now let's take a look at the cosine curve. The graph of y equals cos theta looks something like this. It also repeats every 360 degrees, but crosses the x-axis at, for example, minus 270 degrees, minus 90 degrees, 90 degrees, and so on. So every 180 degrees. The maximum of the cosine curve is also 1, and the minimum is also minus 1. So let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We are first required to sketch the graph of y equals cos x in the given interval. So here's a sketch of the graph. Now if cos 60 degrees equals 0.5, then using the graph we are required to find one other value of x for which cos x equals 0.5. Here we've sketched the graph or the line of y equals 0.5. As you can see, it cuts the graph of cos x twice in this diagram. Once at 60 degrees and once at minus 60 degrees. So cos of minus 60 degrees is equal to 0.5. We're now going to take a look at transformations of trig functions. If we multiply a function by a scalar, then the graph stretches in the y direction. Let's take a look at an example to illustrate this. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We're required to sketch the graph of y equals 2 sin x in the given interval. Here's a sketch of y equals sin x. Let's see what happens when we multiply that by 2. If we double this, we're stretching the graph in the y direction. This is a vertical stretch of scale factor 2. Notice that the amplitude for y equals sin x is equal to 1. Amplitude is measured from the x-axis to the peak of the sine curve. The range for y is a set of y such that y is in the real numbers and y is less than or equal to 1 and greater than or equal to minus 1. We can also see that the amplitude for y equals 2 sin x is 2. And the range is the set of y such that y is in the real numbers and y is less than or equal to 2 and greater than or equal to minus 2. If we multiply the x value by a scalar, then the graph stretches in the x direction. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We are required to sketch the graph of y equals sine 3x, where x is between 0 and 360 degrees. Here's the graph of y equals sine x. Let's see what happens when we multiply x by 3. In effect, everything is happening to the function sooner, so we're compressing the function. Or alternatively, this is a horizontal stretch of scale factor 1/3, as you can see in the diagram. In this example, amplitude remains the same. However, the frequency has increased. Notice that for the curve y equals sine x, there is one wave passing between 0 degrees and 360 degrees. However, for y equals sine 3x, there are 3 waves passing between 0 and 360 degrees. We're now going to briefly look at quadratics. A quadratic equation can be expressed as y equals ax squared plus bx plus c, where a, b and c are real and a does not equal 0. A quadratic will look either like this for a greater than 0, or like this for a less than 0. We will revisit quadratics in considerable detail in another session. And now for exponential functions. These are functions of the form f of x equals a to the power x, where a is a constant. So here's a graph of y equals 2 to the power x. Here's y equals 3 to the power x. And here's y equals 4 to the power x. There is a value n which has a special property. At any point on the curve, the gradient of n to the power x is equal to the value of n to the power x. This is the exponential function e, or exp. It is of the form f of x equals e to the power x. E is a constant value whose value is approximately 2.71828 to 5 decimal places. And it looks something like this. We can find inverses of exponential functions. These are called logarithms. We will be looking at exponentials and logarithms in more detail in future sessions. We are now going to revisit mappings and functions more generally. A mapping will transform one set of numbers into a different set of numbers. It can be described in words or via an algebraic equation. It can also be represented as a graph. A mapping is a function if every input has a distinct output. Types of functions are one-to-one or many-to-one. Let's have a look at some illustrations. We're going to first look at a one-to-one function. So suppose we have a set A and a set B. Each value in set A is mapped onto a value in set B, as shown. This is a one-to-one function. Let's now take a look at an example of a many-to-one function. We have a few values in A, this time mapping to one value in B, as shown here. This is a many-to-one function. We may have another scenario. So in this scenario, we may have one value in the set A mapping to two values in the set B. This is one-to-many, but it is not a function. For a mapping, the domain is the set of all possible inputs, and the range is the set of all possible outputs. Some mappings can be made into functions by changing the domain. For example, y equals root x. Here's a sketch of y equals root x. If the domain is the real numbers r, then y equals root x would not be a function, as values of x less than 0 cannot be mapped anywhere. So, for example, square root of minus 4 in the real plane does not go anywhere. So, if we redefine f of x as f of x equals root x for x in the real numbers and x greater than or equal to 0, this will now become a function. We can equivalently write f such that x goes to or is mapped to root x, where x is a member of the real numbers and x is greater than or equal to 0. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So in this example, we're required to state whether this mapping shown on your screen is one-to-one, many-to-one, or one-to-many. We're also required to state whether it is a function or not. So let's have a go at part A first. Is this mapping one-to-one, many-to-one, or one-to-many? Out of the three illustrations we can see towards the top of our screen, the one on the right fits the bill best. We have one value mapping to two values. Therefore, this is a one-to-many mapping and it's not a function. And now for another example. Again, for this example, y equals 3x minus 2, we're required to state whether this mapping is one-to-one, many-to-one, or one-to-many, and also state whether it's a function or not. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. Is this mapping one-to-one, many-to-one, or one-to-many? If we take a look at the graph, we can see that each value of x is mapping to a single value of y. Therefore, the mapping is one-to-one. Now let's take a look at whether this mapping is a function or not. Remember that a mapping is a function if every input has a distinct output. This is indeed the case for this example. Therefore, the mapping is a function. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So again, we're required to state whether this mapping is one-to-one, many-to-one, or one-to-many, and also state whether this mapping is a function. So let's solve part A first. What is this type of mapping in particular? Notice that each value of x is mapped to one value of y. Therefore, the mapping is one-to-one. Now let's solve part B. We are required to state whether this mapping is a function. Let's again recall the definition of a function. A mapping is a function if every input has a distinct output. However, if we consider 0, we know that it's not mapped anywhere because 2 over x or 2 over 0 does not make sense. Therefore, the mapping is not a function. We can omit 0 in order to make a function. So we can define f of x as f of x equals 2 over x for x in the real numbers and x not equal to 0. Now for another example. Again, for this function y equals x squared minus 2, we are required to state whether this mapping is one-to-one, many-to-one, or one-to-many. We are also required to state whether this mapping is a function. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A first. This example seems to fit the second illustration. Take a look at the diagram for y equals x squared minus 2. Notice that x, for example, maps onto y, but minus x also maps onto y, because x squared and minus x all squared are both the same. So in other words, both x and minus x are mapped to one y value, and therefore this mapping is many-to-one. And now for part B. Is this mapping a function? Again, referring to the definition of a function, a mapping is a function if every input has a distinct output. Therefore, the mapping is a function because each value in the real numbers is mapped onto another value in the real numbers. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A first. We are required to find the range of f of x equals 4x minus 5 for the domain x equals 2, 3, 4 and 5. So let's see where each of these values map onto. 2 maps to 3 because 4 times 2 minus 5 is equal to 3. 3 maps to 7 because 4 times 3 minus 5 is 7. The value 4 maps to 11 and the value 5 maps to 15. Therefore the range of f of x is 3, 7, 11 and 15. And of course f of x is 1 to 1. Now let's take a look at part B. We are required to find the range of g of x equals 2x squared for the domain x in the real numbers and x greater than or equal to minus 3 and less than or equal to 3. We are also required to state if the function is 1 to 1 or many to 1. So let's solve this. Here's a sketch of y equals 2x squared. We of course have x in the real numbers and x between minus 3 and 3. The value 3, as shown in the graph, is mapped to the same value that minus 3 is mapped to. And this value is 18. 2 times 3 times 3 is 18, and also 2 times minus 3 times minus 3 is also 18. Therefore, the range of g of x, as we can see from the diagram, is g of x greater than or equal to 0, but less than or equal to 18. And of course, g of x is many to 1 because we have, for example, in this diagram, as you can see, two values mapping to 1. And that's the case for several values. And now for part C. We are required to find the range of h of x equals 2 over x for the domain x in the real numbers and x greater than 0 but less than or equal to 4. Here's a sketch of h of x. Notice that the minimum occurs at h of 4, which is equal to 2 over 4, which is equal to 1 over 2. The value x equals 4 is mapped to a half. Also, as x tends to 0, h of x gets larger and larger. In fact, it's tending to infinity. Therefore, if we want to find the range of h of x, we would state it as follows. The range of h of x is a half less than or equal to h of x. And of course, h of x is 1 to 1. Let's now take the discussion on functions a step further. We already know what a function is. We have also defined one-to-one functions. These are also known as injective functions. An example of an injective function is given here in the illustration. We're now going to take a look at onto or surjective functions. A function is onto or surjective if every element of the range is mapped to by at least one element of the domain. This can be illustrated in the diagram on the right-hand side. Here, every element in B, which is the range, is mapped to by at least one element of the domain in A. Notice that the function on the left is not surjective. There are 3 points in the range B which don't have any points in the domain mapping to them. Finally, we can now define a function which is bijective. When a function is both one-to-one and onto, we call the function bijective. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to consider the function f of x equals x squared minus 2, where the domain of f is r plus, or the positive reals, and the range is minus 2 to infinity. Determine whether f is injective. We can see this illustrated in the diagram on the right-hand side. We're trying to determine whether the function is injective. So if 2 points do map to the same element, i.e. suppose f of x equals f of y, then we have that x squared minus 2 equals y squared minus 2. Simplifying this gives us that x equals plus or minus y. However, since the domain of f is all the positive reals, then we can only conclude that x equals y. And therefore we can conclude that f is injective. And now for part B. We are required to determine for the same function whether f is surjective. Suppose that y is in the range minus 2 to infinity. Then we need to find an x in the domain r plus, or the positive reals, such that y equals x squared minus 2. This is true if and only if, and we've rearranged this equation, we have that x squared equals y plus 2. Or equivalently, x equals root of y plus 2. The question is, does this root really exist? Now, since y is greater than or equal to minus 2, we have that y plus 2 is greater than or equal to 0, and therefore we can square root it and get a real answer in the real numbers. And therefore, x equals root y plus 2 is in the positive reals. Therefore, every element of the range is mapped to by at least one element of the domain. And therefore, f is surjective. And finally, for part C, we are required to determine whether f is bijective. From part A, we know that f is injective. From part B, we know that f is surjective. In other words, f is both one-to-one and onto. Therefore, from the definition, we can conclude that f is bijective. The inverse of a function carries out the reverse operation to the original function. Elements in the range of the original function are mapped back into the elements of the domain of the original function. Therefore, inverse functions only exist for one-to-one functions. The inverse of f of x is written f inverse of x, as shown on your screen. Functions f of x and f inverse of x are inverses of one another. The graphs of y equals f of x and y equals f inverse of x are reflections of one another in y equals x. Let's illustrate this. Suppose we have a function y equals f of x as shown. Then the inverse function is a reflection in the line y equals x as shown on the screen. The domain of f of x is the range of f inverse of x. So for example, as you can see on the graph, there is a point 0, 3 on the line y equals f of x. This is reversed in y equals f inverse of x. So the point 3, 0 is on the line y equals f inverse of x. And similarly for the point minus 6, 0, or equivalently 0, minus 6. The range of f of x is also the domain of f inverse of x. Let's now take a look at an example. We are required to find the inverse of the function f of x equals 3x squared minus 5 for x greater than or equal to 0. Let's explore this example by means of a flow diagram. So we start with x. We square it to obtain x squared. Then we multiply that by 3 to obtain 3x squared. And then subtract 5 to obtain our function f of x, which is equal to 3x squared minus 5. How do we find the inverse? We find the inverse by going backwards. So if we start with x, we add 5, which is the reverse of subtracting 5, and obtain x plus 5. Then we divide by 3, which is the reverse of multiplying by 3, to obtain x plus 5 all over 3. And finally we square root, which is the reverse of squaring, to obtain square root of x plus 5 all over 3. So if x is greater than or equal to 0, then 3x squared minus 5 is greater than or equal to minus 5. Therefore the range of f of x is f of x is greater than or equal to minus 5. And therefore, since the range of f of x is the same as the domain of f inverse of x, we have that the domain of f inverse of x is greater than or equal to minus 5. And therefore, f inverse of x equals the square root of x plus 5 over 3 for x greater than or equal to minus 5. Now let's have a go at another example. Find the inverse of the function f of x equals 4 over x minus 3 for x in the real numbers and x not equal to 3. We are required to do this by changing the subject of the formula. So let's solve this. We need to rearrange in order to find an inverse function. Begin by letting y equal f of x. Then we have y equals 4 over x minus 3. And rearranging or multiplying through by x minus 3 gives us y times x minus 3 equals 4. And therefore, multiplying out the brackets gives us yx minus 3y equals 4. And if we add 3y to both sides, we obtain yx equals 4 plus 3y. And then dividing through by y gives us x equals 4 plus 3y all over y. Recall that the range of f of x is the domain of f inverse of x. So the range of f of x is in the real numbers with f of x not equal to 0. And therefore, in this example, the domain of f inverse of x is the real numbers with x not equal to 0. So continuing with this example, recall that we had x equals 4 plus 3y all over y. And therefore, we have that f inverse of x equals 4 plus 3x all over x. We've simply replaced the x by f inverse of x, and the y has been replaced by x. We need to check that at least one element works. Let's try 5. Now f of 5 equals 4 over 5 minus 3, which is 2. So 5 gets mapped to 2. The question is, does 2 get mapped back to 5? Let's see when we apply f inverse to 2. If we apply f inverse to 2, we obtain 4 plus 3 times 2 all over 2, which is 5. So 2 is indeed mapped back to 5. And therefore, f inverse of f of 5 equals 5. And therefore, for this example, our function does indeed work. Now for another example, pause the video and have a go. Press play when you're ready to view the solutions. Let's have a go at part A first. The function f of x is defined as f of x equals root x minus 5 for x in the real numbers and x greater than or equal to 5. We are required to state the range of f of x. So let's solve this. The range of f of x is y in the real numbers where y is greater than or equal to 0. Since f of 5 equals 0, and we also have that as x increases from 5, f of x also increases without limit. And now for part B. We are required to find the function f inverse of x and state the domain and the range. So let's solve this. We let y equal f of x. Then y equals root x minus 5 can be manipulated to give y squared equals x minus 5. And adding 5 to both sides gives us x equals y squared plus 5. Now we interchange x and y to give y equals x squared plus 5. And therefore the inverse function is f inverse of x equals x squared plus 5. Recall that the range of f of x is the domain of f inverse of x. And so in our example, notice that f of x equals root x minus 5. And this is of course the positive root. Therefore, the range of f of x is greater than or equal to 0. Therefore, the domain of f inverse of x is x in the real numbers with x greater than or equal to 0 also. Also recall that the domain of f of x is the range of f inverse of x. And therefore, since the domain of f of x is x in the real numbers with x greater than or equal to 5, we have that the range of f inverse of x is y in the real numbers with y greater than or equal to 5. And finally, for part C, we're required to sketch y equals f of x, y equals f inverse of x, and y equals x. So let's solve this. Here's our line y equals x. Here's y equals f inverse of x equals x squared plus 5, which was found in the last part of our example. And a reflection of this in the y equals x line is y equals f of x equals square root of x minus 5, as shown on your screen. This brings us to the end of this session. If you have understood its contents, you should be able to use a function to describe a mathematical relationship, plot functions and identify the nature of a simple function from its shape, including quadratic and exponential functions, work with the equation of a straight line, carry out simple transformations on trigonometric functions, determine the domain and range of a function and whether it's injective, surjective or bijective, and find the inverse of a simple function. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to it.